And now we move on to sampling. Here is an analog signal that we are transforming into discrete levels. So here we have this level here, and here, and here, and here. So these are the binary numbers generated by the analog to digital converter at each sampling point. So if I am transmitting this serially, I would start with 0, 1, 1, 1, and then 0, 1, 0, 0. Remember that we transferred the opposite way, so this is if it's serial. But if we are doing parallel, then we would just, 0, 1, 1, 1, transmit simultaneously like that. Okay? So with 4 bits, we have 2 to the 4 or 16 voltage levels here. Here is 16 voltage levels. Since we start with 0, so therefore we only have up until 15. So the number of levels is 2 to the n, including 0, and the number of increments is 2 to the n minus 1, which gives us up until 15. Although there are 16 levels, there are only 15 increments. So these guys are levels, but these guys are increments. How do I make this more clear? These are levels. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is 16, which includes 0. But if we are counting increments, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Only 15 increments for 16 levels. And then we talked about quantizing error. We know that these discrete levels, these infinite points of the analog signal cannot be translated to digital accurately at some points. So for example, at this point, it is between 0, 1, 1, 0 and 0, 1, 1, 1. So it depends on whether we need to round this up or round this down. But either way, because we need to do the rounding, this causes error. Because why? It's not the actual number. When we're not giving the actual number, we are introducing errors. So this is called quantizing error or quantity error. So quantizing error can be reduced if we divide the analog range into a large number of smaller voltage increments, which means that to the 2 to the power of n, where n is like very huge. Now again, if we have a lot of sampling points or a lot of levels, this means that our application will be more complex, will be more expensive. So we can't just simply do it. To have more increments or levels, greater number of bits must be used. Like for example, if we're using 12 bits, this will give us 2 to 12 levels or 4096 levels. For increments, this will be 4095 increments. So this more finely gives us a better resolution and will minimize quantization error, supposedly. But again, because our analog signal has infinite number of points, it will not eliminate quantization error completely, but reduce it. Okay, so we talked about computing quantization error. So we assume a 10-bit A to D converter, so we have 2 to the 10, 1024 voltage levels or 1023 increments. Assume an input voltage range between 0 to 6 volt. Therefore, the minimum voltage step increment is 6 volt divided by these increments. So we will get 5.86 millivolt for each increment. Therefore, the maximum error that can occur will be half of the LSB value. Now, why did it say half and not the simply just the LSB value? If we go back to the example, right? Go back to our example over here. Remember that we had a value in between these two levels, and it was simply in between these two levels, and therefore the maximum area that we can round off will be, the maximum will be half, because okay, let's say it's 6.3. If it is 6.3, we will round it off to 6. But if it is 6.5, we will be rounding it off to 7. So how do I say this? The maximum, or like the worst case scenario of rounding off, here the area introduced is 0.3. But here the area introduced is 0.5. Here the area introduced is 0.4. So the maximum area that you can actually introduce because of the lack of levels is actually 0.5. Sorry, 0.5. So the maximum quantization error that you can give is actually 0.5 of the LSB, or the increment. I hope that makes sense. So between these levels, the increment is 5.86 millivolt. The maximum area that you can introduce would be half of this, because if the point is here, you're basically giving 0.5 area. If it is here, the maximum that you can give is 0.5 error. So half of the increment will be your maximum error. Alright, now let's talk about computing quantization noise. Quantizing error can also introduce quantization noise. This noise limits the dynamic range of the A to D converter because it makes low level signal impossible to convert. So we can approximate this quantization noise simply by equating it to this formula. 12 is fixed, Vn is the RMS noise voltage, and Q is the weight of the LSB. So how do we calculate the weight of the LSB? So basically, weight of LSB is the increment for your bit. Right? Using the previous 10-bit example, we know that it was 5.86 millivolt. So this is where they got the value. And square root of 12 will give you 3.464. And this will give you a noise, quantization noise of 1.7 millivolt. Therefore, the signal should be digitized 2 or more times this noise level to ensure a reasonably error-free conversion. This is noise. The previous example tells us the maximum error that we can get from quantization, from the lack of levels. This tells us the noise introduced from the error, and we have to digitize twice this noise level. So 1.7 millivolt times 2. And then we also talked about D to A converter. At some point, it is usually desirable to translate the multiple binary numbers back to its analog voltage. So this is the job for the D to A converter. So here this shows the process of converting the 4-bit binary numbers to analog. Of course, it's not perfect. It's very bad actually. So since the steps are rather large, what we get back is more of an approximation rather than the analog signal. And then we also talked about this example, and then we talked about pulse amplitude modulation to sample analog. Right, we talked about this, and then I briefly talked about duty cycle. Now, duty cycle is basically, it tells you T1 over the total period. What is the transmission over the total period? What is the total transmission? Assuming that this is the guy that is transmitting. This is if we have a rather symmetrical transmission. But in this case, we only have positive cycles. So we will calculate the time, we will include the period as the time that it's not even transmitting anything. So this is going to be our T. This is going to be our T. Okay. Now assume an analog modulating signal to be digitized. We would multiply the analog signal with the VC equation to get the following spectrum. Now this is of course a simplified version. Assume, so we started off with an analog, right? And then we want to digitize it. So it will multiply this signal with VC. Now what is VC? VC is simply this guy. Let's go back. It's simply this equation, whereby this equation is the instantaneous carrier voltage. When we multiply the signal or the analog signal with a carrier voltage, what we will get is a series of narrow pulses shown down here, right? We will get these pulses because they are at fixed intervals. So you have D, and then you have, sorry, it's omega s, and then it's at 2 omega s, and then it's at 3 omega s. So this is Fs, 2Fs, 3Fs, and this is the DC component. So you would multiply your analog with this guy, and therefore you will get its representation at the DC, at the Fs, at the 2Fs, and the 3Fs, and so on. So let's go back to the simplified version of this. So here you have your signals, right? You have your signals at Fs, 2Fs, 3Fs from the VC equation. You started off with FM. You multiplied FM with VC. What you would get is this guy, right? Okay, so when you multiply it, you would get a series of pulses, and these pulses are situated at something called the Nyquist zone. The Nyquist zone, right? So the Nyquist zone, we have first, second, third, fourth, etc., etc. So the Nyquist frequency or the sampling frequency is always, the Nyquist frequency is always in the second Nyquist zone. And the Fs frequency divided by 2 is always in the first. Fs is always in the second. Fs divided by 2 is always in the first. So this is fixed. This tells you the zone. And then Fs plus Fs over 2 gives you third. And so on and so forth. 2Fs plus, sorry, and then 2Fs would be fourth. Right? 2Fs is in fourth. Third is Fs plus Fs over 2. Okay, something like that. Now, why is it important to know this? Because the Nyquist zones tell us the best sampling rate that we will talk about later. So just bear this in mind for now. If the sampling rate is not high enough, if Fs is small, then a problem called aliasing arises. I know we talked about aliasing before. We will talk more about it today. Now, alias is a signal that is mistakenly sampled when sampling frequency is less than twice the input frequency. Remember that we had conditions, Fn or Fs needs to be greater than Fm if it starts from 0. Then Fn needs to be greater than 2 BW if it is at the middle. Right? Okay, so aliasing causes a new signal near the original signal to be created. This frequency is Fs minus Fm is called the imaging or the aliasing.